Hi class, this chapter is on motion, describing motion, ultimately talking about energy and gravity. So there's a lot of information here, and this is a lot of this information is what you might see a lot of details of in a first year or a first semester physics course. So I'm assuming that you may have not taken physics, and that's fine. You don't have to have physics. You don't have to know all the nitty-gritty details that you might have learned in a physics class to understand what this astronomy course is trying to teach you. So this chapter is about motion, and the first part is just about describing motion. So the first part of this chapter is about words that we can use to describe how things are moving, how that motion is changing, and what kind of things affect those changes. And then we also want to talk about mass and weight and what the differences are between the two. So these are important definitions. You know, anything in bold is always important to keep in mind. So when we hear the word speed, obviously it's probably the most obvious one. That's, you know, what your speedometer reads on your car, and that just tells you how fast you're going. It doesn't tell you anything about what direction you're traveling. It just tells you how fast you're going. So speed is distance over time, distance divided by time, miles per hour, meters per second. The standard unit in physics, in the sciences, is meters for distance and seconds for time. So 10 meters per second would be a speed that you might consider an object having, and or kilometers per hour as well. You know, you could use kilometers, hours, seconds. There's a variety of ways to write it, but speed is just a how fast you're going. It has nothing to do with direction. All right. Velocity is sort of like speed, but it has a direction. So velocity tells you not only how fast you're going, but what direction you're traveling. So a velocity might be something like 10 meters per second along with this direction. Due east would be the direction. So those two things combined, the speed and the direction, give you a velocity. And then acceleration is how that velocity is changing. It tells you something about how velocity is changing. So it's a change in velocity. And since velocity includes speed and direction, then you could have one or the other or both of those things changing, and you would have an acceleration. So for example, in this first little image here, we have a car traveling in a straight line, and it is accelerating because the speed is changing, going from 30 kilometers per hour to 60 kilometers per hour. So that is an acceleration. If the car is slowing down, going from 60 to 30 to 0 in a straight line, we call that an acceleration as well. But we would refer to it as possibly a negative acceleration, meaning that the negative means that it's sort of opposite the velocity. It's making the velocity, the speed, decrease rather than increase. So we refer to both slowing down and speeding up as accelerations. It's just one might be called positive and the other might be called negative. And then if you have another car, for example, that's traveling at the same speed, 60 kilometers per hour, but it's going around a turn, that is also an acceleration. That's an acceleration because the direction of velocity is changing. So the speed might not be changing, but the direction is changing. Initially, the car is going kind of up in this direction to the upper right, but later on, the car is kind of going to the lower right. So the direction is changing of that car. The speed is not. But because the direction is changing, it is considered an acceleration. So any way we change the velocity, we have an acceleration. So velocity is meters per second in terms of the units, just like speed. The direction is just however you can describe the direction, and there's multiple ways of doing that. Acceleration tells you how that velocity is changing, and the units for that are meters per second squared, or also we can also think about it as meters per second per second. So that's a little bit easier to understand if you think about what gravity does. So gravity, if you ignore air resistance, it's kind of hard to see this, but if you can kind of get rid of the air, and you could do this on the moon if you go there, but if you get rid of the air and you drop objects, you'll find that everything falls at the same acceleration. It's about 10 meters per second squared, 10 meters per second per second. That's what we call little g. G is the acceleration due to gravity. And that 10 meters per second squared means that the speed increases as the object falls, 10 meters per second every second. So again, this acceleration is 10 meters per second per second. So if I initially drop the ball, it doesn't have any velocity initially. After 1 second of time, it has a velocity of 10 meters per second downward. After 2 seconds of time, it has an additional 10 meters per second of velocity downward, so 20 meters per second. So the acceleration is about 10 meters per second every second. If it could fall for another second, a third second, it would have a velocity of about 30 meters per second. And so then maybe it would hit the ground at that point. But so we can continue, it depends on how long the object falls, but eventually it'll hit the ground. But as long as it's falling, and as long as we can ignore air resistance, the acceleration due to gravity will make the object's speed increase by 10 meters per second every second. Roughly 10. It's closer to actually 9.8, but 10 is a good enough number for us. So Galileo showed that this acceleration due to gravity is the same for all falling objects. So he did a lot of experiments. Remember, we talked about Galileo and how he was one of the first scientists to really be a scientist, to really do experiments and to test things. And he showed pretty carefully that no matter what objects you dropped, they all accelerated at the same rate. He was able to do this not by getting rid of air resistance, but by using objects where the air resistance was negligible. So other things that are very important to think about. So we talked about speed, velocity, acceleration. Momentum is another thing. Momentum includes velocity, but it also includes mass. So if you think about two objects, like say a car and a little bug. So a car has a pretty big mass. The mass is kind of a measure of how much stuff something's made of. And that's a very crude definition of mass, but so the mass is like how much stuff something's made of. And so say you've got a car and the car crashes into a wall. All right, say it was traveling at 10 meters per second and it crashes into a wall. Well, it's going to do a lot of damage to the wall, probably, right? Because there's a lot of mass there. But if there's a bug, a little fly or something traveling also at 10 meters per second, it crashes into the wall. Well, the wall's not even going to know. Nothing's going to happen to the wall. And in fact, the bug might be fine too, possibly. And so there's the same velocity of those two objects, but the momentum is very different because the mass is very different. So mass is a key thing to think about when you're thinking about collisions of objects. Not only what happens depends on the speed of something that collides with something else, but how massive that thing is. If you think about a bowling ball and like a ping pong ball, a little tiny ping pong ball that's very light and a bowling ball that's very heavy, if you were to collide those together, the bowling ball isn't going to really feel that collision very much. The ping pong ball will feel it significantly. It'll bounce off in a different direction very easily because it has a much lower mass and much smaller momentum generally. So things with much bigger momenta will kind of feel the collisions less in a sense than things with lower momentum. And we'll talk about collisions and things like that later on a little bit more. But so momentum can change. All right, you can change an object's momentum. So I referred to collisions, two balls colliding. Their momenta can change. Their speed can change generally. Their direction could change. Maybe the mass doesn't change. The objects, when they collide, maybe they don't change their mass. They still remain the same object, possibly. Not always. But, usually the velocity changes. So why does that change occur? Well, it's because there's a force involved. There's a force from one object acting on another object. So if I have a little ball here, let me draw a little ball. So if I've got a little ball here, that ball has some mass, m. We'll just represent it by m1. Maybe we'll describe mass in terms of kilograms, so maybe it's 10 kilograms. And we can say it's traveling this way. Initially, we'll draw a little arrow to represent its velocity. We'll call it v1. So it's traveling that way. And there's another ball over here. Maybe it's a really big ball. I'll give it a big M for mass. Call it mass 2. So that's a big mass. And let's say that ball is just sitting still. Let's just say it's just sitting there on the ground. It's not moving at all. And this ball is coming along and it's moving. We would say that this ball here that has no velocity, so therefore it has no momentum. This ball here has momentum because it has mass and it has some velocity. So what happens is that they're going to collide. And let's just say they bounce off of each other. They don't stick at all. There's various ways that things can collide, but let's say that they bounce off of each other. Well, there's all kinds of possibilities as to what happens, and it mainly depends on the differences between these two masses, M2 and M1. If M2 is really big compared to M1, like this is a bowling ball, and this is a small ping pong ball, most likely what will happen is you'll have big M, M2, moving a little bit. It might acquire a very small velocity because of that collision. Call it V2. Call it V2 final. Put an F there. All right. So it might move a little bit because of the collision. But this little ball, because it has much less mass, there's a very good chance, and again this all depends on the difference in the masses, but there's a very good chance that that little ball, after the collision, will have bounced backwards. So this is M1, M1, and maybe it will be going this way at maybe a slightly slower speed than what it had coming in. M1 final, we'll call that. So it was coming in with maybe 10 meters per second of velocity. Maybe it bounces off with like 9 meters per second velocity. So both of these objects experience a change in momentum, because this guy was initially 0 momentum, and then afterwards this one is moving with a little bit of momentum to the right. And this one was moving to the right, and now it's moving to the left. So those are changes in momentum because there are changes in the velocity of the objects. And again, where do these changes come from? Well, they ultimately come from forces involved. If I were to draw an intermediate diagram, let me draw kind of a line between these diagrams. Should have given myself a little more room. But in between, there's a moment at which the two objects are touching. So the two objects are right next to each other. They're in contact at this moment during the collision. And during that collision, then, the little mass M1 is pushing on the big mass M2, and at the same time, this big mass M2 is pushing on the little mass M1. Those forces involved in that collision are what cause the changes in momentum of the objects to occur. So forces result in changes in momentum. The total force, what we call the net force. So there has to be some net sort of unbalanced force on an object to change its momentum. We can talk about similar things in terms of rotation. Instead of moving left and right or up and down, we can talk about an object rotating. So here I have an object like a disk maybe, and there's a center of the disk right there. And let's just say it's spinning, and I'll draw kind of a curved arrow to indicate what we might call an angular velocity. So the object is spinning at a certain rate, 10 revolutions per second or something like that. That object has angular momentum. It's not moving up and down, left or right, back and forth. So it doesn't have momentum, which we sometimes call linear momentum. It has angular momentum because it's moving in an angular rotational kind of way. So how do you change those kinds of things? How do you change rotational motion? You change it with something called torques. So a force changes linear momentum, left and right, up and down motion. A torque changes rotational motion, changes how fast the object is rotating. Maybe it speeds up the rotation or it slows down the rotation. There's a variety of ways that this could happen. So here's a thing to think about. We'll come back to torque in a minute, but thinking about force, for each of the following, is there a net force on the object described? So a car coming to a stop. A car coming to a stop. Is the momentum changing? That's what you want to ask. Is the momentum changing? And if you say yes, then there must be a net force acting on the object. The car is coming from some speed to a stop, meaning no speed. So there must be a force. A bus speeding up. Well, is the momentum changing? Yeah, the momentum's changing. The speed is increasing. An elevator moving up at constant speed. Well, the elevator's moving up. You might think, well, something's pulling it up. A cable or something like that, so there's a force. Well, yeah, that's true. There's a force in the elevator cable, but there's also the force of gravity trying to pull the elevator down. Turns out that those two forces cancel out. They don't, overall, they don't affect the motion of the elevator. It's moving at a constant speed, straight upward. There is no change in velocity. There's no change in momentum. So there's no total force acting on that elevator. The upward force on the elevator, if I draw that, the upward force on the elevator, here's my little elevator. There's an upward force that we might call a tension force in the elevator cable. That's being balanced by a gravitational force, which we can call like F, force of gravity. Put a little G down here. A force due to gravity. If this elevator cable were to break, then yeah, the elevator would go falling down, and it would be accelerating downward at the acceleration of gravity, 10 meters per second squared. But it's not. It's going upward at a constant speed, and so these two forces they're balancing each other out. The total force on the object is 0. So total force is what's important. How about a bicycle going around a curve? Okay, it's turning. It's going around a turn. Its direction is changing. So its velocity is changing. So its momentum is changing. So there must be a force. A moon orbiting Jupiter. Again, the moon is going in an orbit around a planet. That moon might be a circular orbit, whatever it is. The moon is changing direction, so there is a change in velocity, there is a change in momentum, there must be a net force. So let's see if we're right. Yes, we were correct. So go back, make sure you understand these. If you need to go back and review, go ahead and pause and rewind. So we talked about mass. So what is mass? Well, mass is a measure of, as I said, kind of crude definition, it's a measure of how much stuff is in an object. It's not really the formal definition that we use in physics, but it's kind of, for our purposes in this class, that's fine. And then what is weight? Well, weight is the force that a scale exerts on you. So when you stand on a scale to measure your weight, that scale is pushing up on you to keep you from falling, in effect. And so if you were to pull that scale out from under you, you'd fall down a little bit to the floor. All right, so the scale measures the force that it's pushing up on you with to keep you in place, and so it measures your weight. All right, so let's look at the this little animation. This is from the study area in the Mastering Astronomy site. So here we have a person in an elevator. The elevator's stationary, nothing's going on. They're standing on a scale. All right, the person has a certain mass. There's a certain amount of material the person's made of. The person's standing on a scale, and the scale measures a certain weight, 140 pounds. And the elevator's stationary, nothing's happening. What if we make that elevator go up at a constant velocity? Well, we measure the same force on the person. The scale is measuring the same force on the person. So the scale doesn't really know that the elevator is moving up at all. As long as the elevator is moving at a constant velocity, if it's moving along very smooth tracks, and you might have experienced this if you go in elevators of tall buildings and stuff where the elevator can move for a little while, you don't really notice that it's moving. You might notice the initial movement and the final movement when it speeds up and slows down, but you don't really notice the movement in between when it's moving at a constant velocity. But what if we make that elevator accelerate upward? What do you feel? Think about what you feel, what you have felt in an elevator when you accelerate upward. Maybe if it accelerates really fast, maybe your knees buckle a little bit. Well, if you were to do that with a scale under your feet, the scale would measure you as having a bigger weight. Your weight changed because that scale is pushing up on you harder to make you accelerate with the elevator. All right, you are in contact with the scale, and so it's the scale's responsibility in a sense to push you up so that you move along with the elevator. And so because the elevator is accelerating and the scale is accelerating, it tries to make you accelerate. Trying to make you accelerate means that there's a net force acting on you, an extra little force pushing up on you from the scale, and the scale measures that as an increase in your weight. Now, your mass hasn't changed. You didn't change any material that you're made of, but the measurement of your weight has changed because you're in an accelerating elevator. If you accelerate downward, then the opposite occurs. You don't need as much force holding you up because the whole elevator is falling down to some degree. There's less of a force between the elevator, the scale, and your feet. And so the scale measures a lower weight for you. Again, your mass hasn't changed, but the weight that's measured by the scale has become smaller. Now, what if you were to cut the elevator cable? What would happen? You might see in movies that when people are in an elevator, when the cable is cut, that they go flying to the ceiling. Well, that doesn't happen, because if the elevator cable gets cut, the fastest that anything is going to fall down is the acceleration due to gravity. The biggest the acceleration will be is the acceleration due to gravity. And so, most likely if this cable is cut, there's going to be still some friction along the rails maybe of the elevator, making the elevator not fall completely at the acceleration due to gravity. But certainly the top of the elevator, for example, isn't going to fall faster than what you would fall if you were just simply to fall down the elevator shaft. You're going to fall together. You're just going to float. You will be floating inside that elevator. So let's see the elevator in free fall. There's the floating person. You can do that again. The person floats right above the scale. They don't go flying up to the ceiling. They float right above the scale, and the scale is not exerting a force on them anymore, so the scale measures the weight of 0. You are weightless. So weightlessness doesn't mean that you're not moving, doesn't mean that there's no gravity. It just means that you're basically in free fall. You're falling freely, and the scale is falling with you, and there's no force exerted between the scale and you, and so it reads 0 for your weight. So that's weightlessness when you're in free fall. So here's a question on the moon. what do you think your weight is going to do? Or your mass? Weight is the same, your mass is less. Your weight is less, your mass is the same. Your weight is bigger, your mass is the same. Or your weight is bigger and your mass is less. So which one do you think it is? Well, remember, mass is a measure of how much stuff you're made of. If you suddenly go to the moon, assuming you don't go on a big diet or you don't eat too much, your mass doesn't change, right? So your mass is your mass. That doesn't change. But it's your weight that will change. Your weight is determined by force that a scale is pushing up on you. And if you're just standing there on the ground, that scale is pushing up on you with a force that's being balanced by the force that gravity is pulling down on you with. And so on the moon, gravity is less. The force of gravity is smaller. It's a smaller object. The moon is smaller than the Earth. Gravitational force on you by the moon is smaller. So your weight is going to be smaller. You will weigh less on the moon, but your mass will be the same. You'll still have the same material. So if you think the best way to lose weight, if you want to go on a diet, is to go to the moon, well, yeah, the scale will measure you as having a different weight, but your actual body mass hasn't changed. The actual stuff you're made of hasn't changed. So your weight is less, your mass is the same. And then weightlessness in space. Why do astronauts experience weightlessness in space? Well, it's not because there isn't gravity. There is gravity. When you're in a rocket, that rocket is orbiting the Earth. When you're in a satellite or the space station, for example, it's orbiting the Earth. That orbit can be considered as a continuous free fall. That rocket is continually falling toward the Earth, but it's just traveling fast enough that as it falls, it can go around the Earth. It keeps missing the surface. It never actually hits. So we'll demonstrate this in a second, but you can imagine if you were to sort of jump off this tower, you could run at, there's a little platform here, you could run at a certain speed and jump off, and you would fall a certain distance. You'd fall down, but you'd travel a little bit of horizontal distance as well. If you ran faster off the platform, you could travel a little bit further horizontally. And so if you ran even faster, you could travel even further horizontally. And eventually there's a speed, if you ran fast enough, you would travel so far horizontally that the Earth would start curving below you, and you'd actually be in an orbit around the Earth. Now this, of course, doesn't normally happen with people, but we'll demonstrate this with sort of a fictional cannonball. But that's what an orbit is. An orbit is a continuous free fall motion of an object around the Earth. Being then in that rocket means that you're falling with the rocket, and like in the elevator, you're just going to be floating there inside the rocket. And so it's not because gravity has been turned off somehow, but rather it's because you and the rocket are simply falling. The whole time you're going in this orbit, you're simply falling. So here we have a cannonball up on a mountain, or a cannon up on a mountain, a couple other mountains here. We're looking down on the Earth's North Pole. The Earth's equator is where those mountains are. And I can take a cannonball and fire it at various speeds, so I'm just going to increase the speed a little bit just to start it off. 1 kilometer per second. So that's a pretty fast speed. I'm going to launch this cannonball off the top of a mountain. So let's fire that. There it goes. It travels pretty far. It starts off pretty high above this mountain. It travels pretty far horizontally, but as it travels horizontally, it falls toward the center of the Earth and eventually crashes into the ocean or the ground or whatever. It travels a certain distance. So that's certainly not an orbit. But you should believe me that while it's falling, it's in free fall. If there was no air resistance, you would just be floating there with the cannonball as you traveled with it. You'd just be floating. You wouldn't feel anything until you hit the ground, and that wouldn't be very pleasant. But you'd be floating. You'd be in constant free fall, as if you're weightless, right? As if there's no gravity. There really is, but it's pulling you down toward the center, and you don't really feel gravity until you hit the ground. So let's reload that and increase the speed. Let's go to 3. Fire it. Now we travel faster out of that cannonball. We can travel farther then before we hit the ground. But, clearly we can travel a bigger distance and be in free fall still that whole time. And again, we don't feel gravity until we actually hit the ground. Then we can feel gravity. So we continue to reload and increase the velocity. Let's go to 6. Fire. There we go. We're going really far before we crash. We almost make it halfway around. And so we're still in free fall the whole time, but we're traveling so fast horizontally that we can cover a lot of distance before we actually fall to the surface. All right, so we're constantly falling toward the surface. This path is getting closer and closer to the surface. But because we're traveling so fast horizontally, we travel a very large distance horizontally around the surface of the Earth. Let's go up to 8 kilometers per second. Reload and launch. So now we're falling, and look at that, 8 kilometers per second is right near the minimum velocity you need to maintain an orbit around the Earth. And again, it's just like the previous examples at lower speed. All you're doing is falling toward the center, but in this case you're traveling fast enough that you never actually hit the surface. You're in constant free fall, just like you were in those other examples. So if you were sort of inside that cannonball, you'd be floating inside that cannonball. You would feel as if gravity didn't exist anymore, but in reality it's because you're falling with the cannonball all the time, just like you would be falling in the elevator if the cable was cut. So this animation again is in the study area, and so don't forget to, if you want to play with it, definitely do it. Let's check one more thing though. What if we go really fast? We can go up to, let's say, 10. What happens? So 10 kilometers, now we can travel farther away, but gravity is strong enough. There's still a pull of gravity acting on that cannonball. The higher velocity allows us to get further away from the Earth, but gravity is still pulling us back, and in this case, this particular speed still isn't enough to sort of escape the Earth's pull. So we form an elliptical orbit rather than a circular orbit around the planet. So 10 kilometers per second will form an elliptical orbit. In reality, that orbit would take about 294 minutes to orbit the Earth if we traveled at that speed. And we can continue to, let's reload and go up a little bit more. Let's go to 12 and then fire and see what it says. So we get even further away from the Earth. Aha! 12 kilometers per second says the cannonball will escape into space, never to return again. So for every object, there's something called escape velocity. The escape velocity is the velocity that some object would need to have to escape the pull of whatever it's near. So the Earth, for example. To escape the gravitational pull of the Earth, you'll never get away from it completely, but you'll have enough what we call energy of motion, kinetic energy as we'll call it eventually, to be able to get as far away as possible, to go to infinity and beyond in a sense. So if the Earth were sort of the only thing in the universe to pull on us by the force of gravity, if we traveled at 12 kilometers per second, we would travel out to infinity and never come back to the Earth again. Any speed less than, the 12 isn't the exact number, but we can try 11, reload, and go back and see what it says for 11. But so this one it does give us an orbit, 11 kilometers per second does give us an orbit. In reality, that would be about 2,350 minutes. So somewhere between 11 kilometers per second and 12 kilometers per second is what we'd refer to as the escape velocity for objects on the Earth. That's how fast you'd have to launch them to allow them to escape, in a sense, escape the gravitational pull of the Earth. You can never technically get away from the pull, but you've got enough energy of motion that you'll never actually stop and come back to the Earth. So this is a fun little animation. It's one of my favorites that the book has. So finally, wrapping things up, going back to torque and angular momentum. I had mentioned torque before. Again, angular momentum is this sort of rotational motion, and you could describe it, you can think about it in two ways. Either it's like the Earth rotating on its axis, that there's angular momentum there, or you can think about it as the Earth going around the sun. There's an aspect of angular momentum there as well. So any kind of rotation or orbital motion involves angular momentum. And again, a twisting force, something called torque, is what's responsible for changing that angular momentum, making something speed up or slow down, things like that. So forces change momentum, torques change angular momentum. So to summarize, these are important things to remember. Speed is just different distance divided by time. Velocity is speed and direction. And acceleration tells you how the velocity is changing. And so you can have an acceleration if the speed is not changing, but the direction is changing. Or you can have an acceleration if the speed is changing, but the direction is not. Or you can have both changing. You can have both speed and direction changing. So speed could change, direction not change, travel in a straight line, but speed up or slow down. Speed staying constant, but maybe you're going in a circle. That's an acceleration. Or you could have both, going in a circle and speeding up or slowing down. That, of course, would be an acceleration too. Momentum is mass times velocity, very important in thinking about things like collisions and stuff. And a force is what causes changes in momentum. It creates these accelerations. Mass, we said, is basically a measure of how much stuff something is made of. And again, that's kind of a crude definition. It's not a real formal one that we'd use in physics. Weight is the force of a scale acting on the mass. What is the scale actually measuring? And objects are weightless when they're in free fall. Weightlessness does not necessarily mean that there's no gravity. It just means that you're in free fall. You're floating basically in free fall. If you were to close your eyes, you would have no idea that you're actually falling. You're just kind of floating there. So hopefully this helps helps you understand a few of the concepts. Again, as always, feel free to email me anytime if you have questions. And in the next couple of lectures, we'll go into a little more details on some of the relationships between these quantities that we talked about today.